Yeah, let's get right into it. So, big news. I was later than I wanted to be with these, but still feel like I'm recovering from this big transition. Still getting caught up on a lot of things. But the next homework assignments are out. Maze Solver and Decision Tree. So let's take just a quick look. I don't want to spend too much time on these. We can talk about them during the Q&A if you ask. But the next assignments are out. So let's... which one is my favorite, Maze or Decision Tree? I actually like both of these. The Decision Tree is brand new, and I really like the way that one came out. And Maze Solver is always fun. Maze Solver is probably a little more fun because you get the visuals. But they're both really fun assignments, I think. So Maze Solver, I don't know why I'm scrolling through the doc. I'm not going to read it to you during lecture. But Maze, the goal here is to solve a maze. This is mostly about today's lecture. Today's lecture content is going to show us how to actually approach this problem and how to do this. But I have some player that starts at a specific spot. I want to solve this maze. Well, the way this is set up is wherever I click, I should be moving to that click. Oh, did I actually click on that? I'm already showing off a bug. But you can move into the walls a little bit. So wherever I click, I should go there, and I shouldn't move into any walls like you just saw. But if I click the end, it shouldn't just solve the maze, but it should solve the maze in the shortest path possible. So if you look at this, we have two paths to find the exit. There's one path down this way which just zigzags back and forth, a lot of wasted time, or this path that you did see it take, which is the shortest path to the goal. So I should never be taking this path if I'm going from the start to the finish. I should be taking that efficient path to get there as fast as possible with the fewest amount of movement, the least movement possible. So that's our goal for the maze. And for what it's worth, this is part of, as you see, MMO on the syllabus, on the course schedule. This is set up. Why? Don't you know I'm in the middle? It does know I'm in the middle of the lecture. That's why it's doing it. But it knows I'm demoing this. I've never seen that before. It hasn't done that before. But anyway, this is multiplayer. We can have as many people connecting to this server as possible, as the server can handle, as the hardware can handle, and have all those players moving around in this space. I already finished mine. Yeah, you're not supposed to be able to go through walls. That I haven't even seen that in my testing. It's just because it's in lecture, the code knows it became sentient and wants to embarrass me. I know you can just click on the wall if you're adjacent to it. I don't have a check to say if is that a valid move. That's intentional, but you shouldn't have saw what you saw when we first started. That shouldn't have been the case. I don't know why that happened. But you can't actually go through walls. Only when you're adjacent to it and click on it is the only time you're supposed to be able to move through a wall. Just disable no clip. Yeah, clips are on. So that's the maze. Decision tree. This, we're going to get some data about animals. We have, let me pull it up on GitHub. We have some feature vectors for animals, for certain zoo animals. And we want to use these features to be able to guess an animal that a user is thinking of. So we're building a typical, like a 20 question style guessing game where your user thinks of some animal and then you ask it question after question to determine which animal they're thinking of. And the goal with this, the big challenge with this, is doing that in as few guesses as possible, with as few questions as possible. So if they're thinking of a scorpion, you decide which question to ask. Does it breathe? Does it have a backbone? Does it have teeth? And ask just the right questions to determine as fast as possible what animal they're thinking of. So we have, it should be 21. It looks like it's not quite 21 on this page. But I believe 21, because it's scrolling. 21 attributes. So you can obviously do this by asking all 21 questions and just looking up in the table. There are no duplicate feature vectors. So you just ask all 21 questions and figure out what it is. Well, that's no good for this assignment. That would be a 115 assignment, just parsing CSV and doing it that way. For this, we want to build a decision tree, which is going to start with no information. And then each node, you're going to ask a certain question. And depending on the answer to that question, you're either moving to the left or right subchild and eliminating the animals that don't have the feature that you asked for. If you say, does it breathe? And they say no, then you're eliminating all the ones and then moving in the tree, building the structure of this tree in such a way that the order of the questions you're going to ask is going to get you to that animal as quickly as possible. So we have this running up here. I'm going to think of a worm, I guess. Just thinking of something that I know. Actually, let's just look up something else. How about a frog? Let's say a frog. I don't know if a frog has teeth. I don't think a frog has teeth. I'm going to say no. Maybe this wasn't the best thing. Does it have a backbone? Yes. Is it a predator? It eats flies, but I'm going to say no. I could look it up, I guess. But is it the size of a house cat or larger? No. Does it swim? Yes. It's a duck. Well, it's not a duck, but I answered something wrong there is the problem. Now I'm curious. Frog, toothed. Frogs do have teeth was my big mistake. Does have teeth. Does it have 4 legs? Yes. Is it a predator? I'm going to cheat again. Frog, predator, frog. Yes. So we are counting eating flies and being a predator to bugs as a predator. So yes. Is it the size of a house cat or larger? No. Does it swim? Yes. Does it have a tail? Oh boy, this isn't going great. They have little stubby tails. Does that count for this database? No, it doesn't. No, it's a frog. So a lot of glitches. They're not glitches. I just don't know my animals. Maybe in the maze solver, you accidentally saw one. But when we're focusing on the pathfinding, I'm okay with that. When we do have this as a full MMO, the glitches will be gone. All right. So with that, I just want to make sure everybody knows those assignments are out. The graders are up too. Everything's released for these things. The TAs are working on the videos. I just released these things to them yesterday too, so they need some time to work out the videos. And then we'll have these assignments fully up and running. Yeah, they're not glitches, they're features. All right, so let's talk about pathfinding in a BFS. So thinking about those 2 assignments, the decision tree, you have everything you need to be able to do that. We know trees. We know how to have 2 child nodes from a tree. We got that down. But how do we do that maze solving? How do we do the breadth first search? Or how do we use breadth first search to actually solve that maze problem that we saw? So we saw breadth first search last time. We saw graphs last time. But let's use that to accomplish this goal. Today's lecture question is finding the distance between 2 nodes. Distance we haven't defined yet, but we will shortly. The distance is the length of the shortest path, or at least one of the shortest paths between those 2 nodes. So how long does it take to get from one node to the next in the shortest possible amount of time? So with this, I actually do have a method in that graph class, or rather some bookkeeping data structure that will help you out with this. So this lecture question, I gave you probably a little too much for this lecture question, too much code. So there's not a whole lot to do here, to be honest, since you can leverage what I gave you. But this is what we want to solve for today's lecture question. And then the next step is the full pathfinding. How do you find that whole path? So let's revisit paths and then define distance. So a path is some sequence of nodes for which each adjacent node in the path has an edge connecting them. They are connected by an edge. So this is a valid path in this graph from Lincoln to MIT to Utah to SDC to Rand to UCSB to SRI. All of those are connected by edges, so we're good. We have a full path. The length of a path, which we haven't defined yet, is the number of edges in that path. So however many edges we had to travel, that's the length of that path. So this is a path of length 6 because it took us 6 edges. We had to traverse 6 edges to get to from where we started to where we're going. The distance between 2 nodes is the length of a shortest path between those two nodes. So the distance between, for example, Lincoln and SRI, you can get there in this path of length 3, and there's no path of length 2, 1, or 0 to be able to get there. That is a shortest path. There's potentially multiple ones. In this case, it's the only shortest path. But this is the distance between two nodes, is the length of the shortest path. Rand and BBN, they're connected by an edge. So the distance between those two nodes is 1. It only takes one edge to be able to get from one to the other. So this is our distance, that shortest length of the shortest path between those two nodes. And that's what we want to find for the lecture question today. So how do we find the distance between two nodes, and how do we find that shortest path? Well, we know BFS. We have BFS at our disposal. Let's use that to find the distance between two nodes, and then eventually the paths between two nodes. So with BFS, we just saw the basic implementation of it. Today we're going to see how we can extract some useful information out of BFS. So we run BFS, and instead of just exploring, last time we only explored the connected component and figured out if the graph was connected or which nodes are connected, as the lecture question had you doing, which nodes are connected to each other. But now we want to find that distance and extract more information. So let's take a look at the run of BFS and see how we can extract some of that information that we want. How can we get something useful out of this? So let's start at just arbitrarily some node. I kept starting at UCLA, so I want to start somewhere else here. Let's start at Carnegie, run BFS, and this time, instead of just exploring the nodes and marking which nodes I've explored, now I want to build what's called a DFS tree, or a BFS tree. So I'm going to remember the edges that I traveled when I explored those nodes. So instead of just saying we visited Carnegie, let's mark that as visited, I'm going to add Carnegie to my breadth first search tree, and then add all the edges and nodes to that tree as I explore new nodes. So I'm going to explore Harvard and Case. I'm going to add those edges that I used in my tree, and then add those nodes to that tree. And notably, this is not necessarily a binary tree. We can have more than 2 child nodes, but we're going to represent this tree as a graph to be able to track those nodes and edges. We can put it in our graph data structure. We just don't have any cycles in that graph, so it is technically a tree. Now, when we have Harvard and Case, each time we explore from one of these nodes, we're going to add those edges and nodes to the tree. So Harvard is going to explore BBN, Case is going to explore Lincoln, and we're going to add those nodes to our tree as well, in addition to marking them as explored. Now, Lincoln and BBN, depending on how our queue is set up and how we added these values, how we added these nodes, and just arbitrary choices that our code makes, is going to determine which one of these we visit first. Whichever one we visit first is going to be the one that ends up visiting MIT. So notice that MIT, as we'll see in a few slides, when we're visiting these nodes, we're actually exploring a shortest path between two nodes, and from the start node specifically. So from Carnegie and MIT have distance 3, and there's 2 different ways to get from Carnegie to MIT with distance 3. That's what's going to cause one of these ties and one of these arbitrary decisions. So one of these nodes is going to visit MIT, and the other one just isn't. The other one is going to say, oh, MIT's already visited, I'm not going there. So we have an arbitrary decision. One of these edges is going to be taken, and one of these edges is going to be thrown away. I'm going to say Lincoln happened to be first, and Lincoln ended up exploring MIT. BBN said MIT's already explored, but it did get to explore Rand to get that edge in the BFS tree. Now MIT is going to explore Utah. Rand is going to explore UCLA, UCSB, and SDC. And we can add those to our tree, MIT to Utah, Rand to those 3. And now we have 4 nodes in our queue, depending on which one was visited first. We don't know which one is going to get to explore SRI, but one of them is going to explore SRI. And we can see all of those 3 paths, this path, this path, and this path, are all going to have the same length from Carnegie to SRI. So which one we actually find, which one we use, is arbitrary. To find Stanford, we have to go through UCLA because the SRI to Stanford, that's too slow of a path. But all these are going to find SRI at the same time. So one of them's going to find it. I just arbitrarily said that I think Utah is going to be the first one to find it. And then the other ones, they're saying, oh, SRI is already explored. But UCLA gets to explore Stanford. It still finds a new node to explore. And then at this point, we're emptying our queue. There's nothing left to explore, so nothing really happens. If BBN explored MIT first, would Lincoln just stop searching? If BBN explored MIT first, Lincoln will still look up its adjacency list. So it'll see MIT, it'll see case, but when it checks, it's going to notice that both of them are already explored. For this visual, they're both already highlighted in orange. So it's going to say, since they're both highlighted in orange, I have nothing to do, so I'm done. And then it can tell the program, okay, the next node in the queue, you can start processing that node because I'm done with my processing, which I didn't get to do anything. I just checked 2 nodes and said that they're in the set already, the explored set already. So there's nothing to do there. So at the end of this breadth first search, we get from the starting node at the root of our tree visually, we get this structure which shows how we found every single node in this graph. And yeah, there's and notably there are no cycles here. This is a tree, but there are levels to this. So there are levels, just in the way I drew this, as we usually draw a tree, we have the root, and then each time we travel an edge, we're going to move down visually. When we represent this visually with those edges going down and these kind of branches hanging from the root, then we can picture these levels starting at level 0 at the starting node and then just incrementing the level each time. The level number is exactly the distance from the start node to any node on that level. So as we're exploring this node, we're always exploring every edge that we have come in contact with. If we start at Carnegie and explore every single edge from Carnegie, first of all, the start node to the start node, that's distance 0. If we check from that node and look at every node that we can reach with exactly 1 edge, it's going to be exactly every single node in this graph that's distance 1 from Carnegie. So now on level 1, we have every node that's distance 1 from Carnegie because we explored every single edge. If from those nodes we explore every single node that we can explore from them, then every node that we explore in that next iteration must have distance 2 from Carnegie because we checked the neighbors of every single node with distance 1 from Carnegie. Those must be the nodes with distance 2. And so on. These are all distance 2. If there's an edge connecting any node to these nodes that hasn't been explored yet, notably we're going to ignore Case and Harvard because they've already been explored, but any newly explored node that we find has to have distance 3 because it took 1, 2, 3 edges after exploring every single possibility. It took 3 edges, so that must be the distance. This must be at least a shortest path from Carnegie to that node. The path that we took has to be a shortest path. And however many edges it took, that's that distance. And we do have a shortest path. We have the shortest path from Carnegie, a shortest path from Carnegie to MIT. Go to Case, go to Lincoln, go to MIT. So we get a lot of information by visualizing the breadth first search in this way, by visualizing it in this tree structure as we visit the nodes. So this is how we can get a lot of information out of BFS when we run this thing. But there's still a pretty big problem here, is when we're writing code, we can't just tell our code, hey, just think of it like a tree and it's fine. Then just look at it and tell me the answer. We can't code our machines like that. You're all well aware of that. That's some of the, I don't want to say frustration. I'll stick with feature since we were talking about that. It's one of the features of programming is you might be able to explain how to do something to a human, but training your computer to do that same thing can be very difficult. I like to think of pattern recognition when I think of this. If you look at a picture and I say, is this a picture of a duck, for example? It's a very easy thing for you to do. You can say, oh yeah, that has a duck in it, or no, it doesn't have a duck in it. But how do you write code to figure that out? That is a significantly more difficult problem. So we're kind of faced with the same thing here. I have some visual representation, and I can look at this, and you can look at this and say, whoa, Carnegie to UCSB, that's distance 4, and I can see that shortest path. But how do we train our computers to do that? And for that, we're going to need a little bit of bookkeeping. We're going to use some bookkeeping data structures to get that information out of this breadth first search that we need. Yeah, if duck. If it were only that simple, the world would be a better place. We'd have a lot better software out there. If it were as simple as if duck. All right, so let's take a look at a way that we can actually get that information in our code instead of just being able to visualize it as humans with visual processing centers in our brains. How do we get this to happen inside our computers? So for that, I'm going to introduce a new data structure, and for each node, I'm going to keep track of its distance. I'm going to initialize all the distances to infinity because we don't even know if these are connected or not. If they're not connected, we'll just say that's distance infinity. And the distance of the start node to the start node is 0. So we're always computing the distances and the paths from the start node. The start node is our reference point. Here. So if we want to find the distance between two nodes, we would run breadth first search starting at one of the nodes and then finding the distance from that node to the other node. That's how we would use breadth first search to find the distance between two arbitrary nodes. So with this, we have our starting node of Carnegie, and I'm going to initialize that to 0. I know the distance from my starting node to my starting node is 0 because I'm already there. I'm already at that node. No edges need to be traveled to get there. We're already there. Nothing to do. So this distance is 0. And now every time I explore a new node, I'm going to add its distance to this map. I'm going to do that by adding the distance of the node where we came from by 1. And then that's its distance. We had this distance to get to where we came from. And then we traveled one more edge to get to where we're going. Yep, that's exactly what we're doing. Yep, exactly. Contagious Android. So that's exactly what we're doing. So we're storing a map of all the nodes. And in the code, we'll do this by the node's ID to the distance, the known distance. So we add Carnegie to our queue, and now we're going to process Carnegie. While we're processing Carnegie, we find Case and Harvard. We're going to explore them, add them to the queue. That's stuff we did last time. But we're also going to update this map by saying Harvard, the distance from Carnegie to Harvard is equal to the distance from Carnegie to wherever I came from, in this case Carnegie itself, plus 1. So we're at Carnegie, we took one more edge, and we update those values, explore them, add them to the queue. We're going to process Case next. Case is going to find Lincoln. So when we find Lincoln, we say, well, we found this, we've explored it, so we know it's not infinite distance from Carnegie. But what is that distance? It's going to be the distance of where we came from, Case. So we go to our map, look up Case, we get 1. We add 1 to that. 2, that's the distance of Lincoln. We're going to DQ Harvard, find BBN, and do the same exact thing. BBN from Harvard, 1 plus 1, 2. Lincoln, we're going to find MIT. And MIT, what's the distance to MIT? Well, where did we come from? We're exploring Lincoln's neighbors right now. Lincoln has a distance of 2. Pop that up by 1. The distance to MIT must be 3. BBN is next. We're going to find rand, do that same exact thing. Rand, BBN 2 plus 1 that. MIT is up next. Utah, you get the idea by now. Utah is MIT plus 1. We're going to explore rand, explore all of its neighbors, add those all to the queue. And all of them are explored by rand. Rand was 3, so we pop all those up by 1. All those are distance 4 from Carnegie. Utah is up next. Utah is going to be that one to explore SRI in this case. SRI from Utah was 5. Was 4 plus 1, 5. And finally, UCLA gets to explore Stanford. Distance 5. And we start dequeuing. There's nothing left to explore. UCSB is going to say all my neighbors are explored already. SDC, SRI, Stanford, same thing. All their neighbors are explored. So when they're popped, or when they're dequeued, there's just nothing left to do for them. They check all their neighbors. All their neighbors are explored. Nothing to do. And now we have a data structure that our machines, our computers can understand. This nice map from node to distance from the starting node of Carnegie. Which basically is the lecture question right there. Setting up this data structure, or using the data structure that I set up, which doesn't exactly compute this, but you can use that data structure and leverage that depending on how you want to approach it. But this is the idea of today's lecture question and how we can find the distance between any two nodes in a graph. If anyone has questions, I would. Oh, thank you. All right. Would you use get to get those values? Yeah, you can use get. You can use get or. Wonder if I can pull it up quick. Either get or else, or the. Let me see if I have the right one here. Yeah. No, don't do that. There's BFS. So like here I have a map. This is tracking nodes, not distances, even though I name it distance horribly. But distance, that's my map storing this data. I could go, if I want the distance, the value for node 0 at with ID 0, I can just access it like this as well. And have val d of type int. This is one way to access it. You can use .get, but this you're going to have to actually call get on it to get the value out of that thing, because you don't know if you actually found this value in the map or not. Then yeah, the suggestion is to revert it back to that, or preferably in most cases using get or else. Get or else is going to get the value at this key, but also you can provide it a default option. This is the safest way to do it. If you use get or else, or using get without the .get at the end, and actually using the option the way it's meant to, using a case statement or a match statement. Get or else though is going to get the value at the key 0. If the key 0 is not in the map, it's going to return this as a default value. And then you could say if d equals -1, 0 is not. 0 is not in the map, and you can handle that. And you can handle that appropriately. If you get your default value out of there, your value wasn't in the map, or the value happened to be the default value. Depending on how you have your code set up, you might want that feature. Yeah, this is. If anybody has more questions, please ask them. There's quite a bit going on in this lecture. I'm going to have a tendency to just rip through the slides pretty quick here. I'd also caution a little bit. This is one of those things that might be quite a bit easier to follow in the slides than it is to code it up yourself. So if you have any implementation questions, like the .get question was a good one, let them rip. Because watching the clock, I might be done pretty long before 1:50, but we'll see. Let me just keep going. We'll see. If I get there, I'll take questions and sit there, or just go to Q&A earlier. So that's all well and good, but we have one extra problem that we have. That data structure found us the distance, but if you're working on the maze homework and you say to get to the end, to get to the goal, or to get to the click, this is how many tiles I have to traverse. That's definitely going to get you a 0 on Autolab. You have to actually give the path that needs to be traversed to be able to move that character in the right way. So we don't just want the distance. That doesn't get us where we want to go. We want to actually get the we actually want to get that path itself. So how are we going to do that? We're actually going to store just a little bit different information here. We're going to initialize our initial node to just any default value, any value that we that doesn't mean anything, something that indicates the starting node. And then each time we explore a node, instead of storing the distance, that's why I was wondering why I had a 0 there. That seemed weird. Instead of storing the distance, we're going to store the node that we came from, the node that explored that node. So we initialize our start node just with some value that indicates that this is the starting point. Anything that you know is not an ID in your graph or is not going to be confused for a node, just anything you can write if the value at this key equals this, I know I've reached my starting point. Just something to let you know that. And then each time we explore a node, we keep track of the node we came from. So when we explore Harvard and Case, we're storing Carnegie. This is where I came from. This is the node that discovered me. And we do that throughout the run of this algorithm. So each node, when we're exploring Case and find Lincoln says, oh, it was Case that found me. MIT knows that Lincoln was the one that found it. Rand knows it was BBN that found it. And so on through the whole run of this algorithm. I'm not going to bore you with going through the whole algorithm again. But when we explore a node, instead of saying, okay, who's exploring me? What's their distance? Let me add 1 to it. Instead of doing that, we're remembering which node we came from. Where did we come from? And that's going to help us with the path finding. So now each node has one piece of information. Which edge was traversed to find me? Where did I come from? So we're basically modifying our connected method to count the amount of nodes. Yeah, so for today's lecture question, there are quite a few approaches you can take. You can use your connected. Somewhere in your breadth first search, you have to count how many edges you've traversed to find that node. Or you can do the whole path finding and then take the length of the path. If you're going to work on the maze solver homework, I'd recommend doing the whole path finding, which is actually a big chunk of what I give you. That distance data structure is pretty much this map right here. I gave you a little too much. I don't know why I even have that in the repo. I should give you a little less than that so you get some more practice before diving into the homework, but it is what it is. But yeah, you can modify R connected. So for the maze, our code basically scanning the entire maze of its nodes, and then after scanning, it physically moves. Yeah, I have some slides on that. I'll talk a little more in depth about that. But you want to run breadth first search to find the path, and once you have the path, you're going to find how to traverse over that path. So there's 2 parts to it. Given a path, how do you set your velocity to move along that path? And given 2 points, a start and an end, what's the shortest path that you should take to be able to connect those 2 nodes? So there's 2 parts going on there. So, oh yeah, this is an actual college lecture. But if you're not in the class, you're more than welcome to hang out. You're more than welcome to learn. And so now, how do we find that path? We have all these previous nodes. Where did I come from? Values. But how do we use this to actually find the path that we want to explore? So for this, we're going to take whatever node we want to find the path of. Yeah, thank you, Ruslana. We must have got it linked from somewhere, recommended from something. So we want to actually find that path that we need to take to get from Carnegie to some node. I'm just going to pick an arbitrary node. I'm going to pick the longest path because it's the most interesting, and find our path that we should take to be able to navigate that. So I'm going to start at the end of my path and build this thing backwards. So I'm going to take each step looking at my data structure and build this path one edge at a time. So from Stanford, what was the second to last step? What's the second to last node in this path that we're going to build? So from Stanford, to get to Stanford, we came from UCLA. So to build my path, I'm going to start at the ending point, look up how it was explored, find UCLA, and then I'm going to look up the next one. Well, how did I get to UCLA? UCLA was explored via Rand, so I'm going to add that to my path. Rand, how did we get here? We found Rand through BBN. Add that to the path. BBN, how did we get there? We found that from Harvard. Add that to the path. We found Harvard from Carnegie. Add that to the path. How did we get to Carnegie? Well, Carnegie was our start node, so that must be the start of our path. And when we build this by prepending each node that we look up in this table until we find the start value, we can reconstruct our entire path by using these previous values. These values of where did this node come from? Where did this node come from? And we could do this with any node in the graph, any node we start with. Just iterate MIT to Lincoln to Case to Carnegie, that was the start. And we can find a shortest path from the start node to any node that we choose by iteratively looking up values in this data structure until we arrive at the starting node. What is a node? So node is getting a little overloaded now. Node used to mean an object, exactly, an object that has a value and has a reference to other nodes. The theory is still the same here. We have some value, some entity that has a value and connections to other nodes. But now the node itself doesn't know about those connections. We kind of moved one layer up when we talked about graphs, up the abstraction. And now a graph stores all of the nodes and all the edges between those nodes, those connections separately. So the nodes got a little dumber at this point. They just know their value. And then the graph knows the connections between those nodes. So for a linked list, it was a node has a reference to another node, has a reference to another node. Like we could represent this as a linked list. A tree had a reference to two other nodes. And now a graph, we hit that other level of abstraction. We have nodes with arbitrary connections to other nodes that we're working with. But a node, in short, is something with a value, and then we add structure by adding these connections, which we call edges in graphs, which we call references in trees and linked lists. So BFS, it depends what you mean by automatic. I was hallucinating. Yeah, no, they're automatically. So BFS automatically finds the shortest path if we keep the distance information stored as we search. Yeah, I mean, I'd argue your wording a little bit. It's not automatic because you have to keep the distance information that you search. But BFS, the way that the queue, because we use a queue specifically, which makes it BFS and not DFS or just a generic connected component traversal algorithm, the way that we use a queue and explore nodes, that specific structure gives us this property that whenever we explore a node, we're always exploring it via one of its shortest paths. That's one of the beauties of BFS. It's why we're using BFS instead of DFS right now, because we can get this shortest path information out of just the natural run of BFS. We keep track of this information, and we can extract that nice information out of a BFS run. How efficient is the process for pathfinding? Pretty damn efficient. You can't, theoretically, you cannot, provably cannot do anything more efficient than this. It is the most efficient asymptotically. You can't do any better. Notably, though, this is only for paths, the shortest path in terms of the number of edges. If we have to find the shortest path in terms of edges with weights, if these weights had costs associated with them, which we call a weighted graph, then we have to use other algorithms. That's where your Dijkstra's, your A-stars, your Bellman-Ford, that's where those algorithms come in. Specifically, we're finding the shortest path in the term of number of edges. This is the best you can do. This is the most efficient you can do. It's an O of n plus m algorithm. If you're doing anything asymptotically faster, the proof goes you haven't looked at the entire graph even. We're asymptotically equal to the size of the graph. You can't do better than that because you just haven't even looked at all the nodes and edges yet at that point. So the proof is pretty straightforward with that one. At least the hand-wavy proof. Prepending is how you made the adjacency list, right? Yep. I mean, you could append... I mean, the details can be different. Do they typically use node implementation or graph implementation? They'll use the graph. So the node implementation was for linked lists and trees. If they're doing linked lists and trees, they're using those nodes. The graph, if you have a graph data structure, if that's what you're using nodes for, you would use a graph. So both are used out in industry, depending on what the application is. Okay, so this still doesn't get us where we want to go. We still have one more step here. That's all well and good for graphs. We can find the shortest path between two nodes in a graph. But we don't have a graph. We have this thing. We have this grid map with this 2D grid, and we want to find the shortest path in this grid system. How the hell do graphs help me with this problem? That anyone who's tracking, unless you already know the answer, I guess, this should be the question on your mind right now. How the hell does that UCLA and Harvard stuff help me here? So I'm not going to do the whole solution for the homework, obviously, but I want to get you started on how to approach this problem. This input, this grid that you're given, this map, you can take that information and build a graph out of it. So if we think of each tile on this map as a node, and we write some code to take in the game map and build that graph, then we can convert our problem that we have into a problem that we have a solution for. We want to convert this into a graph problem so we can run BFS on our current location and find that shortest path through this grid system. So if each tile, which is a grid location in the code, we create a graph of grid locations and give each one of these nodes a unique ID, now we can run breadth first search. And if you're wondering, this is the slide that took me the longest to make. There's probably a better way, but I painstakingly placed each one of these. You can probably tell it's really wavy because I did not place them all exactly, but this slide took way longer to make than it might have been worth. So when we do that, when we're playing the game, we see this. When I show my solution to the game and have this thing moving through this graph, we see this, but our computers and our algorithms are going to see this. This is all our BFS sees, is some graph with nodes and edges. In fact, it won't even have this structure, this spatial representation, how it looks like the grid. That's completely lost on the computer too. This will just be some graph. So we want to build this from this, and then our computer, we run BFS on this. If we're doing this right at the start, we run BFS on this node, and then we check this node. Okay, what was the path that you found to this node? And that's going to find us the path from here to here, the shortest path, and then we can have our character traverse that path to be able to make it to that goal in the shortest distance possible. Which brings us to our lecture question. So when we... Stop doing that, you're embarrassing me. I don't know why. I never saw that in my testing. I got to do some more testing, apparently. Or I can blame Windows. It worked fine on my Mac. So when I click, we're going to extract the node for that click. Actually, let's pull up the starter code for this. So there's two methods that you have to implement for this one. The first is going to take two grid locations and the entire map and return that path that should be taken. So all of this is strictly in grid locations, and the app code that you're given is going to find these grid locations for you. So the player location is at a specific grid tile with an XY coordinate, with 0, 0 being in the upper left. We have a grid location for this player, and then whenever we click, the starter code is going to find out exactly where that was clicked. Let's see if I can find it quickly. It's going to take the double values and figure out exactly what tile was clicked on based on that mouse click event, and then send that tile to the server. And by the time, I keep clicking on that. By the time you get it in your code, it's just going to be a map tile with an XY. Oh yeah, I clicked away from it. It's going to be a map tile with an XY. So you have, forget it. So you have the XY grid tile of your current location. You have the XY location of your target tile, and you have the entire map, specifically map tiles that are either passable or impassable, which you have a Boolean to be able to tell if you can pass through a tile or not. So you want to take the entire map, build your graph based on that, with connections connecting any two adjacent tiles that are passable, add all those edges, and then run BFS on your current location. And then after BFS runs, look up in your data, your bookkeeping data structure, take the end tile and work your way backwards to find that shortest path that needs to be found. And then even if it's some complex path, like there visually, I might have thought to go through here, but the algorithm is saying, no, it's way quicker going here. This back and forth is almost traversing the entire length of this map twice. We don't want to do that. No, stop embarrassing me with that. Did I actually click on... Maybe I actually did click on the wall. Which is a simple check. I would have to add a check to say, did the user click on a wall? I'll add that for the MMO, but for this assignment, you don't have to worry about that one. And then you can assume that the click is valid. And then the other method is, given a path and my current location, what should my new vector be to be able to traverse on this path? And there are specs in the document to say exactly what behavior that should have. But given it's not broken code. It is, like, I know why that happened. Some of those I guess I don't. But it's a feature you wouldn't want in the game. I'll give you that one. But yeah, so given that path and my current location, what velocity should I take to be able to traverse on that path? I think it is. Yeah, it's just whenever I click on an impassable tile. Because I don't have any checks for that. I just didn't think it would have that behavior. But it is what it is. At least I know how to cheat in my own game. What if the destination tile is unreachable? For your homework assignment, you don't have to handle that. Obviously, my solution here doesn't even handle it, and I got the big 1-0 in Autolab. So clearly, I'm not testing for that one. But when we move to the MMO, when we start building on top of this, at least for lecture examples, I'll make sure we don't have that feature. But yeah, whenever I click an impassable tile, my code's all broke. It's all jank.